Okay, right. Now, yeah, big data is one of these big buzzwords that people are, into. And then there are firms that claim that they do this big data analytics and so on and so forth. So I think even you as engineering students might be interested in this field. And it is a good field. It is not just good, it is very lucrative in the sense that, people make money out of it. And not that, of course, you're going to be engineers one day, but again, the field is open. So one of my friends who actually graduated with me from my same batch from the University of Peradeniya, went to University of Missouri, Washington at St. Louis, and he graduated with a PhD in physics and then joined data science. Now he's a data scientist at Amazon. So, I mean, for engineers, even for mathematicians, for physicists, we all have chances in data sciences if we can, learn a little bit. So whatever you learn from your degree, plus a little bit more of data analysis, you can go there. And then one of the biggest things is, of course, big data. So my first question from you is, what is big? When you say big data, what is big? Okay, type in your responses and let's see. And just don't be afraid to be wrong. I mean, you can say the whatever, it doesn't matter. Just don't be afraid to be wrong. Type some answers so that we can build up from there. So go to the browser and then type the answer to the question. When you say big data, what is big? Glad we are seeing some responses. Okay, so data collection that has huge volume, high dimensional data. Data cannot be handled by conventional data handling. Okay, so I think all these three would be really nice, three nice places that we can start on. Okay. Data collection that is a huge volume, high dimensional data, which can, so let's actually have three things: big volume, big dimension, big computational resources. So those three are pretty big. Okay. Thank you very much for the responses. Okay. Now let's also go and think about, like, about 10 years ago, this word big data, or two words, big data, was not a thing. So all of a sudden we are, seeing big data analytics, or methods to do big data analytics. So why all of a sudden we are getting this big data? So give some examples where you can see big data being generated. Okay, let's see. So image recognition. Okay, search engines like Google, social media, websites on the internet, stock market. That is one area that, and then social networks, natural language processing data from social media, online media streams. So there's a lot of things where you can see that there is big data. There's a huge volume, high dimensional data that is coming out from these things. And not only these, and even if you consider medical data, like we had we are still having this COVID pandemic. So we have the number of patients and all the attributes, and all these generates billions of high dimensional data that is kind of hard and challenging to analyze and interpret. I think so after the advent of digital age, that is in 2002, that is when all the analog data was surpassed by the available digital data. I think big data is coming more and more to the forefront. And even in physical science experiments, like whatever you do in the Large Hadron Collider, they have these huge, massive amounts of data. In fact, if you actually look at all the data generated at the Large Hadron Collider, it is actually exceeds the whole amount of data generated so far by everything else. So, but we don't really consider all the data. We are only considering 0.0001% and then interpreting that. But still, we are going to get huge amounts of data. Now, yes, of course, now we know that big is large volume, high dimensional, computational challenging, and it comes from everywhere. And my third question is, when you when you try to do analysis of big data, what are the problems that you encounter? So you have probably learned a little bit of statistical methods, so that you know a little bit of statistics, and probably you know more statistics than me. So you have done a little bit of machine learning and all these things. So what are the problems that you have learned in class or in practice that comes with big data, analyzing big data? So computational complexity need a lot of processing power, difficulty to related to size, interpreting the data, of course, like visualizing. I mean, we are living in a 3-dimensional world. How I can visualize 15-dimensional data, complex systems for managing data. So all these problems comes as challenges when handling big data. Okay. So thank you very much for your responses. I'm going to move forward. Okay, so just in summary, just what you have written there. Big in big data can refer to the size, the complexity, or the dimension, or anything, you know, there might be other thing. And in the digital age, big data is generated all over the place. Okay, even when I'm talking, even when I'm using the phone, everywhere you can see use of big data. And the analysis can be a challenge because there are multiple factors involved. Some of them are computational capacity, and then we call this curse of dimensionality, which is problems that arise when the dimension is large, and then problems in interpretations, visualizations, all these other type of trying to, you know, get meaning to the data. Okay, so I think we all agree on these points. Right. So let's actually talk about how can we help. That is, how can topology help? So in order to do that, we want to actually talk about what in the world is topology. Okay. So topology is the mathematical study of shapes that do not alter under continuous deformations. So think of it this way. Now you have a circle. Okay, so think about a circle. So imagine in your mind, you have a nice circle, and by a circle, I mean there's nothing in the middle, only the line, okay, only the curved circle. Now just take that circle and then stretch it. And when you stretch it, the geometric shape of circle is no longer there. Okay, what do you get? You get an ellipse. So geometrically, you have now different shapes. However, in topology, we don't consider things change under these continuous nice deformations. So in topology, we have ellipse and the circle to be the same space. Okay, it might sound a little weird. Okay, but for us, ellipse, circle, and not just ellipse and the circle, but even the triangle not filled in, or the square and the circle and the ellipse are all the same shape. So you might think, okay, so if I consider all these shapes as the same, I mean, there's no different. I mean, what is the distinction between shapes if I consider circle, ellipse, the triangle, and the square to be the same shape? Now, not all is lost. Okay, so if you consider the circle and the ellipse, it is still in one piece. Okay, so that is called connectivity. So it is still connected. So that's a topological property that is still there in the second shape. And then the dimension is not destroyed under continuous nice transformations. So we call these homeomorphisms. We don't really worry about big words. Okay, and then the number of holes. So the circle has one hole, the ellipse has one hole, the empty square has one hole, the empty triangle has one hole. So that is not going to change when you do these continuous nice deformations. If you think about the figure of 8, it has 2 holes. That means it is not topologically same as the circle. And then you have another thing called orientation, that is how twisted it is. So we'll come to some examples. So this twistedness is also a topological property. So these properties, instead of the curvature or the smoothness of the curve or the arc length or the area volume, these just go out of the window. Connectedness, dimension, the number of holes, and orientation comes to the forefront. Okay, so it is one of the subjects actually has beginnings with Euler in the 17th century. And now I believe you as engineering faculty students, you have done real analysis in your first year. And you have done a little bit of linear algebra. I don't know exactly which year, but probably in your first or the second year. So you have done 2 main branches of pure mathematics, at least glimpsed 2 main branches of pure mathematics in the sense of analysis and algebra. So there are 3 main branches of pure mathematics: analysis, algebra, and topology. So topology is a third branch, but it is a relatively new field and it has many applications inside math as well as outside. But because of its relative novelty, as well as perceived hardness, I mean, as a topologist, I find it very intriguing, and I don't really find it any harder than any other branch of mathematics. But people think it's hard. So with that, we don't really teach it until you hit your third year in the mathematics honors program. So now you're going to learn a little bit about this third main branch of mathematics, that is topology. Okay, now before going far, I want to share a little video with you. So I'm going to share my screen, but again, I know that sharing screens with videos is going to be not that successful. So I'm going to just type the video in the chat box. So if you want to go to the chat box and look at the video yourself, feel free to do that. I will play this and I'm going to return in about 5 minutes. And I'm going to ask some questions at the end of the video, so please watch.
What do we think of when we hear them? We might think of spreadsheets. We might think of cell phone GPS records. We might think of internet traffic, or we might even think of DNA sequences. All these sources provide very large and complicated data sets to analyze. How do we make sense of large arrays of numbers in columns and rows? Existing methods for studying data sets typically proceed by asking very specific questions of your data. But let's think about the whole problem a little bit differently. Suppose that our data is divided into groups. Let's represent each group by a node. And let's also represent the relationships between the groups by connections between the nodes. Now what we see emerging here, instead of an unstructured mass of numbers, we instead have a kind of shape or network, which is really representing the shape of our data. We can now use our visual system to look at the data. And identify features in the network which correspond to patterns in the data. These patterns are what we mean when we say extracting knowledge from data. The methodology I've been describing for you is called topology. Topology is the subfield of mathematics that concerns itself with the study of shape, and it has its origins in the 18th century with the Swiss mathematician Leonhard Euler. Euler became aware of a challenge problem concerning the 7 bridges crossing the river Pregel in Königsberg in Old Prussia. The question was, can you stand at the end of one of the bridges, walk across each of the bridges in succession, and return to where you started and cross each bridge exactly once? Now, what Euler did was really extraordinary. He took all the information about the bridges and the river and the islands and land masses and converted it all into a simple network. And in doing so, he found that in fact, it's not possible to walk across all the bridges exactly once. Topology has been studied as part of math for its own sake for the last 250 years. But what's very exciting is that in the last 15 years, we have found that it has applications to many different real-world problems. One of those is the analysis and understanding of high-dimensional and complex data sets. This new area of study is called topological data analysis, and it's changing the way that people are able to understand and analyze their data. There are three big concepts about topology that give it its power for analyzing and understanding shape. The first one of these properties is called coordinate invariance, and it refers to the fact that topology measures properties of shapes that don't change even as you rotate the shape or maybe change the coordinate system in which you're viewing the shape. The second big property is called deformation invariance. So a property of shapes is said to be deformation invariant if that property doesn't change, even though I might stretch or squash the shape without tearing it. Humans are really good at recognizing deformation invariant properties. That ability is what allows us to recognize that a letter A is a letter A, no matter what font that letter is written in. Thinking this way can also lead you to some surprising conclusions. For example, that a donut is very much like a coffee cup. The final property is that of compressed representations. Suppose we have in front of us a sphere. That's infinite amounts of information, which is very hard for us to process and understand. On the other hand, suppose I approximate the shape by an icosahedron. It's still very much like a sphere, but now it's represented by a list, a simple list consisting of 12 nodes, 30 edges, and 20 faces. The focus on connectivity and continuity information allows topology to recognize patterns in data, which make that data relevant. The three fundamental properties combine in very striking ways to allow one to analyze and understand very large and complicated data sets. But this is only the beginning. Topological data analysis represents a fundamental advance in machine learning. In the near future, machines will help humans organize, simplify, and understand their very large and complicated data sets. This partnership between man and machine will have impact for all areas of human endeavor.
Okay, right. So I hope you are still here. Yeah. Okay, cool. Now I would like to ask one question. So if you have watched that video, it talks about three ideas in topology that would help understand data in a better manner or analyze this, data that would give us different interpretations. So my question is, according to the video, what three features of topology allows it to gain insights from data? Okay, you can go to your browser, and it's a multiple choice question. So let's see. Okay, so I'm seeing this. The E is winning. Actually, it is because we didn't start with dimensionality reduction. It would the properties of topological ideas that we use would help us to reduce the dimension, but it is not built in. What we have built in is coordinate invariance, deformation invariance, and compressed representation. Coordinate invariance means we don't really look at, we don't really worry about what kind of coordinates do you have your data. And then deformation invariance is what I said, like when you stretch or bend or twist, as long as you don't tear it, it's fine. And then compressed representation is things like spheres or circles can be represented by something called complexes, which is much more simpler than the actual representation of these shapes. So it's answer E, coordinate invariance, deformation invariance, and compressed representation. So I see that most of you got it. Probably you might be thinking about dimensionality reduction. It happens, but it is not built in. Okay. So let's actually meet some topological spaces. Now, again, remember, we only think about things that are not changed under continuous transformations. So the first one is very easy, the dot. It's a single point. So I mean, in a regular class, I might have gotten these answers from you, but it is connected, so it's all in one piece. The dimension of it is 0. And there is no holes in the dimension 0, 1, or 2. And orientable, so orientable is like, is it twisted altogether or not? If no, it is orientable. Okay, so yes, so that's a dot. So keep in track, keep your mind in these different types of spaces, because we are going to find out that we can actually differentiate between these spaces using TDA. And then the disk, which is a dot but bigger. So actually I got this shape by just stretching that dot. It is connected. Dimension is 2, which means there are 2 degrees of freedom. Actually, it has an area. Okay, it has an area. Holes, 0 dimensional holes, there are none. No holes in the 1 dimension, no holes in the 2 dimension, and it is not twisted, which means it is orientable. I'm asking questions, okay? So just keep track on these objects. The circle. Now, circle is this thin line, which means it has no area, which means it has only 1 dimension. It is all in one piece, so it's connected. It has no 0 dimensional holes, but it has one dimensional hole. That is this hole in the middle. And then 2 dimensional holes, none. And is it orientable? Yes. Okay. Moving on. 2 circles. Okay. Now, this is not connected. So you can see there's this divider. The dimension is still 1. It has thickness, but no, it doesn't have any thickness. Okay? It has length. Holes. Now there's this little surprising thing. It says dimension 0, 1. That is, I will come back to that later, but really the dimension 0 holes are the number of connected components minus 1. Okay. Dimension 1, there are 2 holes. Dimension 2, no holes. And it is orientable. So we have dot, disk, circle, 2 circle, and 2 circles. Now this we call figure of 8. That means the 2 circles are touching, or you can call it infinity shape. It is connected, unlike the 2 circles, which was not connected. This thing is connected. It has dimension 1. Now it is connected, 0 dimensional holes are not there. Dimension 1, there are 2 holes still. Dimension 2, no holes, and it is orientable. So we have seen still orientable spaces. What are the non-orientable? Well, we have to wait. And then we have 2-dimensional spaces, which means it has an area. And this thing is an annulus, or you can think of a short cylinder which has a hole in the middle. It is connected. The dimension is 2. No 0-dimensional holes, one 1-dimensional hole, that is the circle, and then no 2-dimensional holes, orientable. Mobius strip. I think if you're into mathematics, you might have heard this. In fact, you can actually make it right where you live. Take a piece of paper, and when you make the annulus, what you do is you would take a long piece of paper, strip of paper, and then paste 2 edges without any twist using a sellotape. The Mobius band, what you do is you take a piece of paper and paste it after going 1 round, but just before you paste it, do half a twist. Now there are many videos in YouTube discussing fantastic properties of the Mobius strip. For example, if you cut along this red line, Okay, you will see what happened. I'm not going to tell you because I mean, if, even for me, when I did this for the first time, it was a revelation. It was unexpected. So I would like you to, make your own Mobius strip and then cut it along this red line to see what's happening. It is connected all in one piece. The dimension is 2 because it has an area but no volume. It has holes. One hole, you can see there's one hole. You can actually use it as a band. And there's no two-dimensional holes. And you're going to see that this is twisted. Therefore, it is not orientable. Okay, now let's go for a question. So you saw the annulus. That was the annulus. And then you saw the Mobius strip. And you can see all the topological properties that we are worrying about today's presentation. And tell me one difference between the annulus and the Mobius strip. One topological difference between the annulus and the Mobius strip. Excellent. The annulus is orientable while the Mobius strip is not. Annulus is orientable and the other is not orientable. Good, good, good. Okay, great. We are seeing some good responses. Guys, I'm thinking that I'm not giving you enough time to do these responses. I mean, in an ideal world, it would be nice to wait till everyone, try at least to give a good response. So I think this one right here, it's actually obvious. Annulus has one edge. Actually, Annulus has two edges. Mobius has one edge. I mean, that was an excellent response. Can we just give an applause to that student or the fellow learner? And let's actually go and see. So the annulus, you can see that there's a top edge and the bottom edge. And the Mobius strip has, if you can see, if you follow along the edge, the top edge and the bottom edge are combined so that you can get only one edge. Okay, so that's actually an excellent answer. And then another thing is annulus has two sides. The Mobius band has only one side. Okay, so whenever someone argues you with like there is two sides in every argument, just as there are two sides to everything, just show that person a Mobius strip and say that there are things that only have one side. Okay, the Mobius strip only have one side. Okay, cool. Let's move on. Thank you for the responses. And when you have other objects like the sphere, which has a two-dimensional hole. Now, one-dimensional holes are things like circles. Two-dimensional holes are voids, empty spaces in the middle. So it is connected, two-dimensional, no zero-dimensional holes, no circles. So even if you draw a circle on this sphere, you can actually shrink it so that it becomes a non-circle. The dimension, and then there is a void, and it is orientable. Okay, the torus, it is connected. So this is the space, the shape of a donut. Okay, it's a shape of a donut, but there is nothing in the middle. If you want to think about another shape like this, it's a tire tube. So there is air, so nothing in the middle, but it's a tube shape. Okay, it is connected. It has dimension 2, and it has no zero-dimensional holes, but it has two one-dimensional holes. Now, you might be wondering where are the one-dimensional holes. I will come to that, but you can see this little black circle I have drawn on the torus that you cannot shrink into a non-circle. So that is a non-trivial circle, and there's another circle that goes around the horizontal of the torus. So there are two circles in one dimension, and then there's a void in the middle because it's a empty tire tube, and it is orientable. And the last shape that we are meeting today is called the Klein bottle. It is an analog of the Mobius strip in the higher dimension. Unfortunately, you cannot make a Klein bottle in our dimension because it is going to self-intersect, and Klein bottle does not self-intersect. However, it is, you can do it in the fourth dimension if you know, if you're lucky to live long and travel into the fourth dimension, you are going to see an actual Klein bottle. Okay, it is a connected shape, two-dimensional. It has very similar to the torus. It has two one-dimensional holes and one two-dimensional hole, the void. And is it orientable? Just like the Mobius strip, it is not orientable. Okay, now let's see whether you were following me. First question: what are the topological differences between the torus and the sphere? Okay, so let's go to the torus. This is a torus. And then this is the sphere. There is one major difference between these two. And let's see. What are the topological differences between the torus and the sphere? The torus has two one-dimensional holes, while the sphere has none. Excellent. Okay. In fact, the first answer is correct. The torus has two holes, two one-dimensional holes, while the sphere has none. So we will come to that. It has no one-dimensional holes. Okay, cool. Now let's move on. Now we last one. What are the topological differences between the torus and the Klein bottle? The topological differences between the torus and the Klein bottle. So they are very much similar, except for one thing. The Klein bottle is not orientable, and the torus is orientable. Very good. Okay. So let's move on. Okay, so now we have the summary of this section. So we learned a little bit about topological spaces, and you can see that shapes have different topological features. And if you distort a space continuously, you stretch it, you bend it, you compress it, we will not change the topological properties. And if the topological features are different, then the shapes are different, which means something that has no one-dimensional holes cannot be topologically same as something that has two one-dimensional holes. And then the things that you learned, some topological features that you learned are connectedness. Everything is in single piece. N-dimensional holes, whether it is twisted or not. And the last thing that is the dimension, which we call the intrinsic dimension, which means some spaces, if you look at the numbers, it might be 15 parameter, like huge data, but it has intrinsic dimension of 3. Think of a data that represents a hand, but you have added some ambient dimension of 15. Still it's a hand, so it's 3-dimensional. So the intrinsic dimension is topologically unchangeable. So now the idea is, if there's a way to identify some topological features, we can infer things about the data. So that is where we are heading. So now we know some topological spaces and some topological features. The next thing is okay, now we know the topological features. How can we use this in data? Okay, cool. Now, before going to the next section, I just need to see how you guys are doing. Let's have a little mental break. Let's wait for a minute or two. Let me know how you feel. How are you following this presentation? And what have you learned? I'm going to wait for about 10 responses to come in, and then also take a little break. I mean, just a break on your chair, okay? Just stretch out. Okay, let me see. Okay, very topological. Okay, cool. Thank you. So going well so far. Okay, I mean, I can see the participation is slightly dropping, and I mean that's very typical. I'm very apprehensive of these type of online presentations, because you do 2 hours and nobody, all of a sudden nobody is there. I mean, it's cool that you have stuck around. So let's now talk about why or how can you apply this in data. Okay, so this is the workflow of topological data analysis. Okay, now you have this is a very simplified, overly simplified workflow. That is, I mean, right now, this is not what is happening in the on the ground. So ground game is little different, but I think every topological data analysis class, we are going to do this data flow. Okay, so you always start with raw data, that is a point cloud. Okay, sometimes this might have some connectivity. It might be vectors, so we can do it with vectors. It can be graphs, so we can do it with graphs. But let's actually think about a point cloud. And you can see, like, even with your bare eye, that this point cloud, I'm hoping that you can see this presentation. Okay, so this first picture, that you can see there are 3 circles. Okay, so you can see it from your bare eye that there are 3 circles. Okay, now that is your raw data, but probably this is 15 dimensional, so you can't even visualize it. And if it is 15 dimensional, projections might not work to give you that there are 3 circles. Now what you do is you make something called the simplicial complex. So that's the first step. So going from raw data to simplicial complex is the first step of TDA. And then once you have the simplicial complex, you can tell a computer how to compute the homology. Okay, so that is just once you have the structure of the simplicial complex, it's not that hard to compute the homology of the simplicial complex. And you can see that there are some unknown things, like unknown symbols, like integers to the power of 6. I'm going to explain that soon. And then once you do the homology, you compute, once you have it, you do various topological summaries. The one that you see on the top is called the persistence diagram, and one that you see on the bottom is called the persistence landscape. And you can see there are 3 dots in the persistence diagram. So those 3 dots actually correspond to the 3 circles that you can see from your human eye on the raw data. So we are going from this point, the raw data, to this point where we can see, okay, 3 circles. Okay, so I think that's, I mean, when I saw it, I thought that was very cool. Okay. So the question is, does raw data have topological features? Let's think. Now look at these 2 data sets. Okay. Now, what do you think? What topological features will differentiate these 2 data sets? So without even knowing what topological features are, but you know, like 1-dimensional circles, 2-dimensional circles, connectedness. They are only points, they are not lines, but the 1-dimensional holes, the number of 1-dimensional holes, now they are just points, of course, but you can see that if you really squint and look hard enough, you can see that there is, on the first data set, you can see a circle, and on the second data set, you can see 2 circles. So topologically, those are different. So how can you actually make 1 circle in the data set 1 and 2 circle in the data set 2? I mean, if you, of course, if you can actually join them by edges, you can see there is 1 circle here, and if you join them by edges in a nice manner, you can see there are 2 circles here. So joining by edges is kind of the answer, but you have to do it in a nice manner. Okay. Now this is a point cloud. Okay, these are point cloud, but we have to convert it to topological shapes. This is how we do it. So let's actually compare the point clouds and topological spaces. Now, point clouds are not very interesting. Okay, it has discrete topology, so that is not very interesting. No one cares. It has finite but large volume of data. It might lie in a very high dimensional space. On the other hand, topological spaces has interesting features. It is not discrete, and even though it is high dimensional, the intrinsic, the actual dimension can be low. Okay, right. So how do you convert data to topological space? So let's actually look at that. So this is the second section. How do you convert data, raw data, to things that have shapes? So it's very easy. You take a data cloud. Okay, if you want to reduce the number of points, now there are topological in the TDA, there are ways to do it, and if you do machine learning, you might also have ways to do it, like using bottleneck distances versus time distances, those things. But there is a way to reduce, even though the reduced one, you still have significant features remaining. And then what you do is you pick a radius and draw a ball of radius around each point. So you say, I'm going to pick radius 5 or radius 0.1 and draw a ball. And what you do is, if two balls intersect, you join them by an edge. Okay? If two balls intersect, join them with an edge. If three of them intersect, but all three of them do not intersect, draw three edges. Okay, so it's like a triangle, but not filled in, because filled in means all three intersect. But in this case, all three do not intersect, but they pairwise intersect. If all three intersect, draw a triangle, fill in the middle. Okay. So you keep doing it. What about 4? If 4 of them intersect pairwise, then you draw 4 edges. If 4 of them intersect, but not all 4, 3 at a time, then you draw triangles, fill in, triangles, fill in. If all 4 of them intersect, you draw a solid tetrahedron. Okay, so those are the rules. Take the data set, draw balls around it, see whether how many things are intersecting, and follow the rules so that you get these shapes. The only shapes you get are points, edges, filled in triangles, and solid tetrahedrons, and combinations of these. For example, you cannot get a unfilled triangle, but you can get it as a pasting of 3 different edges. So the fundamental shapes are points, edges, filled in triangles, and solid tetrahedrons. We call them simplices. Okay, we call them simplices. So 0 simplex is a vertex, 1 simplex is a edge, 2 simplex is a filled in triangle, 3 simplex is a solid tetrahedron. And it is very combinatorial in the sense that this is where you have this compressed representation. So this thing is the same as a disk, but it can be denoted by just 3 points, A, B, C. And the simplices can be denoted easily using a set. So the set that consists of the vertex A is the vertex A. And then when you say square bracket AB, that means the edge joining the vertices A and B. 2 simplex, that is the triangle, that would be square bracket ABC, and so on. So when you do that for a data set, you will end up getting a combination of simplices, which we called a simplicial complex. So a simplicial complex, it consists of multiple simplices, and the process described above will always give a simplicial complex. Now look at this diagram over here. Okay, so what you see here is okay, so you see the edges A and B, edges AB, BC, and AC are there. And then you have the triangle CDE, which is filled in. So how can you express this as a simplicial complex? AB, BC, Actually, it is CA, sorry, AB, BC, CA, and then CDE. Okay, so we don't write ABC because ABC would mean it is a filled in triangle. It is not a field. You don't see a filled in triangle ABC. So it's AB, BC, and CA, and then you have CDE. Okay, let's try an example. I'll give you a little bit of a time. Find the simplicial complex structure of this figure and express it like this previous one. Okay. So one hint, you can see two filled in triangle and one edge. Okay, this second answer is correct. AC, ABD, and CDE. Excellent. Okay, so that means you're learning something. Good. So yes, AC, that is the AC edge, ABD triangle, and CDE triangle. Good. Okay, now we have done 2 steps of our presentation, of our workflow. Started with raw data, we generated the simplicial complex. And you can see that these actually tell you, okay, that the circles are already showing. Okay, so the next step is, we can't see any of this happening, but we can see, if I give you a data set and it gives you this simplicial complex, the computer will tell me that it is consisting of AC, ABD, and CDE. And because of the number of letters, I know this is an edge, this is a filled in triangle, and a filled in triangle. That means I have 1, 2 simplex, and 1, 1 simplex, and 2, 2 simplices. Okay, I just need to, before we go, because the next section is the only theoretical section, and the only, probably I might say, the things that you don't know section. So I think you need a little mental break for about a minute. And also I would like to see how are you following this section, and do you have any questions up to this point? Actually, this is an excellent question. So here we see the simplices for different radii. How do you decide which radii are more meaningful? That's an excellent question. The answer is, there is no one radius that would give you a meaningful answer. For example, in this one, the middle one gives you the most meaningful answer, because you can see that there are 3 circles, and then also there are 3 circles. In the first one, you can't see the 3 circles. And also in the fourth one, you can't see the 3 circles. But what we do is we just keep increasing the radius, and then we actually plot. We plot it, and we are going to see that you are going to see 3 significant dots and a bunch of noise. So the 3 significant dots are going to be the 3 significant topological features. But I think it's a great question. There is no one radius that would give you any meaning. So you have to look at the persistence topological features. Okay, so that is, I think, probably one of the best questions I have seen in this presentation so far. So keep asking questions. Good. So let's actually go forward for the next section, that is homology. Is counting holes and more. Okay. This I'm still doubtful whether I should do this or not, do the derivation or not. I think I'll do it because again I wanted to show that even if these ideas are new and probably you guys are, I'm just like at the expense of people dropping out, I'm going to do it and see whether you are still following after the derivation. So homology gives a way to count the holes. Okay, so at the end of computing the homology, you're going to see that for this diagram, you're going to see that the homology has rank 3. That means it has 3 circles. Okay, now the reason why I don't really, I'm doubtful whether I should do it or not is because even mathematics graduate students, not just mathematics grad students, like, mathematics honor students or mathematics special students, we don't even teach homology for them because it's a very theoretical construct. Okay, but nevertheless, it is very computable. It is like people can compute it quite soon once you know enough details, but it actually combines algebra and topology. So whenever something that combines algebra and topology, like 2 main branches of mathematics, things are going to be a little out of the place. I mean, you're going to see it a little difficult rather than compared to what you have learned so far. Okay. Right. So homology is a mathematical rigorous tool that computes information about spaces. Okay. So not just for every topological space you can have homology. For when you fix a single space, you can see there is a homology group for every dimension. Okay, so that can give us information about the space in all dimensions. For example, you can see actually these 3 spaces and the corresponding homology. Okay, so the R value is the radius with which we draw the ball. Okay, now H0 means the number of connected components. Now you can see in the first picture, there's this big connected component and 1, 2, 3, 4, 5 dots. So altogether 6. So the 0th homology is 6. The second picture, you can see one big blob and 1, 2, 3, 4. So altogether 5. So the first 0th homology is 5. And in the third picture, you see one component. So the homology is 1. Okay. And H1 gives you the number of circles. So the first one, you see one circle. So H1 is 1. The second one has 2 circles. These 2 little triangles doesn't count because they are filled in. So 2 circles. So H1 is 2. The third one, you get H1 is equal to 3. Okay, now a very quick derivation. Okay, now the problem I encounter here, if you had known a little bit about what's a group, I could have gone with this, but I believe you don't know what a group is. So just think of a group as integers. Okay, integers is a group. And then when you take integers to the power n, that is the product of integers times integers times integers times integers, that is called the free group of rank n. Don't worry about the word, it is integers to the power n. And then we do this thing called chain complexes and boundary maps. Let me actually show you an example. Okay, so ready? This is the only place where we do a derivation. Bear with me for that, okay? Let me just rotate this. 180 degrees, okay. All right, so we are going to do the derivation for this thing. Okay, and the vertices are A, B, C, and the edges I'm going to name it X, Y, and Z. Okay, and because there are 3 vertices, okay, so vertices are 0-dimensional. So the 0-dimensional chain group is integers to the power 3. That 3 comes from because there are A, B, and C. And then the 1 dimension, in the 1 dimension, you have 3 edges, X, Y, and Z. Because there are 3, X, Y, and Z, the chain group is again Z3. And then there are no 2-dimensional things. And there are no, you have to stop at 0 here. So this is called the chain complex. Okay. Now, these functions are called the boundary maps. So boundary, boundary, and boundary. And we usually denote it by the dimension of the domain, like what this thing. So this is boundary 0, this is boundary 1, and this is boundary 2. Okay, and there are 2 things of this map. So bear with me just 5 minutes, okay? Just 5 minutes of math, and then we are off, okay? 2 things. We are interested in 2 things. One thing is kernel, and the other one is image. Kernel is what part of the domain would go and hit 0. Okay, so if you think about these 2, the kernel, everything in the kernel would go and hit 0. Okay, and the image is from the previous map, what would come and hit, like everything, where does it go? Okay. So when you make this complex, the boundary maps, finding the boundary maps is very simple. Okay. So what is the boundary? So if you consider the edge X, the boundary of edge X is A and B. So the boundary map would be just B minus A. Okay. For the edge Y, the boundary map would be C minus B. For the edge Z, it would be A minus C. So it's not that hard. Boundary 1 of X is equal to B minus A. Boundary 1 of Y is equal to C minus B, and boundary 1 of Z is equal to A minus C. Okay. And the kernel means what in the image goes to 0, what in the domain goes to 0, and image is what would hit me from the domain. And we will get this equation, we will get the inclusion, that is image of the previous is always inside the kernel of this. Okay, so just bear with me for 3 minutes. Okay, right. So let's actually find these kernels and images. Okay, so kernel of boundary map 0, image of boundary map 1, kernel of boundary map 1, and image of boundary map 2. These 2 are easy to find. The boundary map 0 goes to 0, therefore everything would go to 0. Therefore, everything will go to 0. Therefore, this is going to be everything. And image of boundary map 2 Boundary map 2 starts at 0, so it can only go to 0. So image will be just 0. So these two are good enough. Finding these two is a little bit tricky. That is, I don't really expect you to understand this part, but I think at least one or two of you will understand. Let's see. So image means I want to see what would happen inside. Okay, so I would like to know. So image of boundary 1, what would happen inside here? So X and Y and Z would go and sit inside here. And then kernel of this guy, that would mean what would go to 0 from here? What would go to 0 from here? Okay. Now, if you think about 0, 0 will go to 0. But are there anything else that would go to 0? Now, if you add actually add these three, B minus A, C minus B, A minus C, you are going to get 0. That means boundary map of X plus Y plus Z is equal to 0. Not only the boundary map of X plus Y plus Z, any multiple of X plus Y plus Z is going to be 0 when you take the boundary map. So this kernel is generated by the element X plus Y plus Z. So that is a single element. Because it's generated by a single element, it is integers. And finally, image. If you think about boundary value of X, you get B minus A. Boundary of Y, you get C minus B. When you take boundary of Z, you can actually express it as boundary of X plus boundary of Y, everything minus. I'm really sorry about this unclear. I mean, the video is not quite clear. But what happens here is these two determines the image. So image is generated by two things, which means this is Z2. So H0 is equal to kernel over image, that is Z3 over Z2, that is Z. H1 is equal to kernel over image, that is Z1 over 0, that is Z. I might have done these calculations in a hurry, but you're going to get integers and integers as your homology. Okay, now coming back to this means it is in a single piece and it has one hole. Single piece, one hole. Okay, and you can see how a computer can, so you are better with computer than me. So you can see how we can give this to a computer and computers can tell you these computations immediately. Okay, so let's go back to the presentation. Okay, so even if the computation is not very clear, what you can understand is that the homology gives you geometric interpretations. So again, because we have a hard time of saying Z and Z2, we just compute the rank. That is, this is 1, this has rank 1 and this has rank 2, which means for that we have a number. It is called the Betti number, that is named after Enrico Betti. Okay, and the zeroth Betti number, that gives you the number of connected components of the space. For example, this has one connected component, so the Betti number is 1. This has two connected components, so the 0th Betti number is 2. Moving on. I have a question for you. Now, you don't really I'm pretty sure about 99% of you did not understand the derivation of homology, but just tell me, by looking at this data set, what is the rank or the zeroth Betty number of this data set? Four. Excellent. Because it has 4 connected components, the zeroth Betty number is going to be 4. Okay, cool. Moving on. The one-dimensional homology is the number of circles, so that we call the Betty of 1. So you can see this particular shape, ABC triangle, that has 1 hole, so Betty of 1, whereas this last uh, shape has a Betty number of 3. And then a two-dimensional homology gives you the number of voids, that is the number of 2D holes, and the torus, it is 1, the sphere, it is 1, and if you consider the join of two spheres touching each other, there are voids in each of them, so that is 2. Okay, cool. One more break. Let me know how things are going so far. By spheres, do we mean solid spheres? We mean hollow spheres, empty in the inside. Okay. By spheres, do we mean? We mean hollow spheres. Okay. Thank you for the question. Okay. So in the summary so far, we start with the data cloud consisting of points. Using a radius, we find the corresponding simplicial complex. And then we compute the homology of each of the simplicial complex, which gives the information about the shape of data. Now we are in the last step. So that is what the student asked there. How significant are these topological features? So that would be given by the persistent homology. It's a topological summary of important features of data. So look at this data cloud. It looks like a circle. It is not a perfect circle. There are some noise. Okay. And the only significant one-dimensional homology is the circle in the middle. So you can see the circle in the middle, but you can, if you look into the data, you can see there might be some more circles. So those circles are noise, and the big circle in the middle is the circle. So one radius is not going to capture that middle circle. So what we do is you take all the radii. So what we do, this is what we do. So this is the original data cloud. We take d equals 0.2, and you can see the middle circle is not even captured yet. When you increase the diameter, you can see the middle circle is now there, and it is captured by the homology. We further keep increasing the diameter, 1.4, still there. And when you have diameter 2, it is gone. So what happens is, at a certain diameter, this middle homology gets born, and that diameter is between 0.2 and 0.6. Let's say 0.4. And then at a certain diameter, this thing dies away. So let's say 1.4 and 2, it's a very random point, 1.6. Okay, it's not, I know the middle is 1.7, but I just want to say it is not the middle point. Okay, so born at 0.4, dies at 1.7. But if you look at the other circles, they can born at any point, but immediately they would die away. So there is one thing that, and then you are going to plot birth versus death. When you see the diagram, you can see this single dot that is above and far away from the diagonal, that is born at 0.4 and dies at about 1 point something. And you can see all the other things are noises, which means the only significant feature of this data set is this single thing. So when you are given this diagram, you know that there is a circle in the data set. Okay, so this is the idea of persistent homology. Instead of computing the homology of a single simplicial complex, just do it for bunch of radii. Okay, I'm going to say 0 0.2, 0 0.225, 0 0.335, 4, and so on. You pick your interval and do it continuously. Plot the birth time and the death time of the homology, and then you can get the persistence diagram, and on the diagram the dots that are further away from the diagonal are the significant features, and the dots that are on the diagonal are the noise. Okay, now probably the last question of the session, I don't know. Let's go. Think and answer. I'll give you about 1 minute. So you have a data cloud that has two circles. Okay, and then you compute the persistence diagram, you get a bunch of noise, and then you get two significant features that tells you there are two circles. Now which dot represent the circle 1, which dot represent the circle 2? A represents circle 2, good. A is the smaller circle, B is the bigger circle, because further away you go from the diagonal, the more significant the features are. So A is the smaller circle, B is the bigger circle. So A 2, B 1. Excellent. Okay, now we are there. We have the workflow in topological data analysis. You have raw data, you make a simplicial complex, you compute homology, and you use various topological summaries to get information about the data set. Okay. Right, just 1 minute video that you can go and watch. I will update the link on the chat box, so you can also go to the chat box and watch the video.
How much do you know about your data? Your data may be the biggest asset of your business, but what if its sources are user activities, sensors, or texts? Current business intelligence systems do not allow you to segment or discover patterns in such data, so you're left with just one option: complex code. That's it. Imagine you could transform your data into a data map in just a few clicks, and without specialist knowledge. Data Refiner puts the power in your hands. Using machine learning, it groups complex data into clusters and allows you to discover things in your data that you haven't even started looking for. You are in control of the results. You can identify anomalies, predict behavior, target audiences, or eliminate engineering errors. The patterns in your data are visualized to make them clear to everyone, from data scientists to business users. You can comply with GDPR and easily explain the results within your organization to clients and regulators. Discover the unknown. Sign up for a demo.
So this is actually one of these things I saw. Now there are a lot of firms that do topological data analysis for a living, and it is not a single tool that works for everything. It is mainly used with other statistical tools so that you can get better insights out of data. Okay, so this data refiner, when you go to their website, you can see that they do deep topological data analysis. Okay. All right, so to end the session, let's do some computations, okay? So if you have your Python console, I think you can join with me. I'm going to do this just one. Okay, so the package I'm going to use is called scikit-TDA. So if you're working with machine learning, you know the package scikit-learn. So this is the TDA package that is this is an easy to handle Python package for implementing TDA for non-topologists. If you want to install it using, you use pip install scikit-TDA, and there are multiple packages RIPSA is the one that computes the homology. So it is the only one that takes a lot of time. Everything else is fine. Persim, it generates the diagrams. Checkmate. Now there are other things that I didn't even touch on, like how to fine tune the simplicial complexes and so on, and the Kepler mapper, and then that is visualization tool. And then you have TADA sets, that is synthetic data sets that you can get, okay, circle, let's see circle, torus, let's see torus, and so on. Okay, so let's actually do one data set. I believe you can see my screen. Okay. Okay, so if you want to do a Python console, do it with me. So if you have scikit TDA installed, you import RIPSA, takes a little time. And then you import the persistence diagram tool, which is persim import plot diagrams. And then, of course, it's a matplotlib thing, so let's do matplotlib. Just in case, import numpy, and then the data set thing. Okay, now let's actually draw a circle. Now, drawing a circle is done by using TADA sets. So let's say, let's give a variable a name that is the sphere, and I'm going to do a one sphere, and one sphere is a circle. So this is a circle. So I'm going to say data circle is take from the package TADA sets, the d-dimensional sphere where I have 1000 data points, dimension is 1, radius is 3, and I can add some random noise. So I'm going to say noise is 0.1. Okay, so when you see, like when you add noise, you can see there are changes that also can be significant figures of the data. And this is what takes time. Now I'm going to tell RIPSA, okay, find the simplicial complex and compute the homology. So this part would take a little time because I have multiple windows open, and also my computer is not the fastest one around. But again, this scikit TDA package is a very rudimentary package where you can do, I mean, you can do computations, but they have not optimized for speed. But there are there are a lot of other packages available where you can do this in a considerable amount of time. So, I mean, it took a little bit time, but yeah. And let's draw the persistence diagram. So this is what you see. Okay, so when you look at the persistence diagram, you can see that there is a, so H0 is given by blue and H1 is given by orange. And you can see that there is single significant blue dot that tells you one connected component. And then there is a one significant orange dot that tells you one circle or one dimensional circle. So I hope you can play with this. You can add more noise and see what's happening. You can add more noise and see how stable is this thing. Okay, so when there is noise, so I have added a lot of noise. So if you can actually plot the circle and see that even a human eye cannot distinguish the noise. But you can still see that even though it is not too high up and you can see a lot of noise here, the topological feature is still there. Okay, and with this you can do a lot of playing around. You can do multiple shapes. Okay, and if you go to scikit website, you can find out all the other shapes that you can play with. Okay, So this is the circle, and you can see the one-dimensional hole in orange. The double circle, you can see there are two holes in orange. And if you take the torus, you can do the torus with the data set, and you can see the two circles. And then in the second dimension, the voids, that is given by this green dot. So that gives you, it is different from the double circle. And then the sphere, again, you can see a lot of noise. For some reason, this gave me two dots here, but it should be like nothing too far away. It was a noisy circle, and then you get this significant feature of the second dimensional hole. Okay, all right. Okay, so that is it. So in this presentation, you learned what topology is, what the workflow of topological data analysis is, and then saw how it can be applied for synthetic data sets. But where is it applied? You can do protein classification. So this is one project I'm working on with one of my friends who's doing chemistry, and he's doing this protein docking things, and the shape of proteins is going to be quite important. And then you have, if you go to, I will share some links with Yashod so that he can send some videos of how this is being applied in protein classification. Okay, so you do a topological collapse, and then you classify proteins depending on those types. And protein shapes matter. I think some of you might be interested in using this. And this is like huge computations. And algebraic topology can help us unlock the connection between neurological structure of the brain and the function of the brain. Now, this is one of the videos in PBS Infinite series that I will also share in the chat box. Okay, I don't know whether Tree Blue One Brown has any videos on topological data analysis, but he has some cool videos on topology. He had one in Bosu-Coulomb theorem and another one in inscribed rectangle theorem. I think because of you are engineering students, you might be interested in Tree Blue One Brown videos. And then analysis of bank or blockchain transactions. So you look at the ledgers or you look at bank accounts, and you use topological data analysis, and then you look at anomalies, like how fraudulent transactions, they have different geometry than real transactions, and then you inform the banks. And then user activity segmentation, things like users who register on Saturday night will pay the most price, things like that. There are statistical method called A/B test. So you can reinforce A/B test. So things like Netflix and Amazon use these kinds of algorithms all the time, and more. Okay, so I wanted to focus a lot about the theory behind topological data analysis, because I mean, even if you go, because you are more applied people, you will immediately learn how can you handle TDA and how can you infer data and infer things from TDA. But on the other hand, because you are not topologists, I think it's better to at least have a glimpse of what kind of theory lies behind this method of analyzing data. Okay, so just a couple of things before we leave it. So I believe you can now define some ideas behind topology, like connectedness, dimension, number of holes, classify some basic shapes like torus, sphere, double torus, understand how ideas in topology can help us interpret big data, define the key steps in the workflow, write a simple program, and tell me some applications where TDA has been used in real world scenarios. So if you are able to do this, I think we have accomplished our learning task for today. Okay, and just a couple of things. If you want to learn more, there is a YouTube channel called Applied Algebraic Topology Network. Applied Algebraic Topology Network. And you can go to Scikit-TDA and play with things. Not just Scikit-TDA, there's like a lot of advanced tools like topology toolkits, Persim, Perseus, and there are R packages, there are MATLAB packages, there are Java packages, all of these things for computing the persistence homology and other things. And then there are companies based on TDA like IST, and then the data refiner. I haven't searched the internet for this, but there might be even more startups that use TDA in their work. Even like stock market data, the things like time series, you can analyze time series and look at things that you cannot see by traditional time series analysis by looking at something called a sliding window embedding. You can look at the topology of the sliding window embedding that can tell you a lot about the time series. And if you want to learn homology, there is, I will send you this presentation. There's this video called You Can Learn, You Could Have Invented Homology Yourself. Okay, so by Bobak Tree, and then also Three Blue, One Brown, some good videos they might have, but not probably for topology, but I don't know. Okay, so you know, okay, cool. And then just a plug. Uh, if you are interested in learning more mathematics, so I know some engineering students, I mean, they go for these lucrative careers, but then there are 1 or 2 people per batch who would be really good at mathematics and they want to learn some more pure maths. So good news for you, we are going to start a master's program in pure mathematics and applied math. So mathematics, you can pick pure or applied. We are going to start soon at the Postgraduate Research Institute, Postgraduate Institute of Science at Peradeniya. So if you're interested, we are going to take our first batch around August, and we can learn topology, we can learn topological data analysis, we can learn group theory, mathematical analysis, and a lot of numerical analysis and scientific computing. It's a 1-year program, and if you want to do research, you can have 1 more year. And we actually planned this program so that we can send our students, general students, special students, SOR students, and engineering students. If they want to pursue their higher studies in mathematics, it is a good starting place. So if you're interested, you can email me at ashwini.pdn.ac.lk. With that, you've been very patient for 2 hours. I see a little drop of participants, probably like half of you have gone, but other people, and even for the people who are gone, thank you very much for being here and for giving you a piece of your time. I wish you all the best in your future education, and keep in touch if you want to work with any kind of topology. I'll be here. Okay, thank you very much.